Welcome to this lesson on the conservation of angular momentum. Today, we're going to explore one of the most fascinating phenomena in rotational motion, why spinning objects speed up when they pull inward. You've probably seen this with ice skaters performing elegant spins on the ice. Let's dive into the physics behind this amazing effect. Angular momentum is the rotational equivalent of linear momentum. Just like momentum measures how much motion an object has in a straight line, angular momentum measures how much spin or rotational motion an object has. It's calculated using the formula L equals I times omega, where L represents angular momentum, I is the moment of inertia, and omega is the angular velocity. Think of it as a measure of how much rotation is happening in a system. Here's the key principle. When no external torque acts on a system, angular momentum remains constant. This is known as the conservation of angular momentum. Mathematically, this means L initial equals L final, or in other words, I1 times omega 1 equals I2 times omega 2. This principle tells us that the total angular momentum before any change must equal the total angular momentum after the change, as long as no outside twisting forces are applied. Let's imagine an ice skater beginning to spin with their arms stretched outward. In this position, the skater has a large moment of inertia, which we'll call I1. This is because their mass is distributed far from the axis of rotation. With this large moment of inertia, the skater spins at a relatively slow angular velocity, which we'll call omega 1. This is the starting point of our demonstration. Now watch what happens when the skater pulls their arms close to their body. By bringing their arms inward, the moment of inertia decreases significantly to a smaller value, I2. But here's where conservation of angular momentum kicks in. Since angular momentum must remain constant and the moment of inertia has decreased, the angular velocity must increase to omega 2 to compensate. The result? The skater spins much faster. This is the dramatic speedup you see in figure skating performances. Let's look at the mathematics behind this. We start with the conservation equation. I1 times omega 1 equals I2 times omega 2. If we solve for the final angular velocity omega 2, we get omega 2 equals the ratio of I1 divided by I2, multiplied by omega 1. Since I1 is greater than I2, this ratio is greater than 1. This means omega 2 must be greater than omega 1. In simpler terms, when the moment of inertia decreases, the angular velocity must increase proportionally to keep angular momentum conserved. The key to understanding this phenomenon lies in the moment of inertia. Moment of inertia depends on how mass is distributed from the rotation axis. When the skater's arms are extended, mass is far from the axis, creating a higher moment of inertia, which makes the system harder to rotate. When the arms are pulled in, mass is close to the axis, creating a lower moment of inertia, which makes the system easier to rotate. This change in mass distribution is what drives the change in rotational speed, while keeping angular momentum constant. Here's the essential takeaway. When a spinning object pulls its mass closer to the rotation axis, angular momentum stays constant, but the rotation speed increases to compensate for the decreased moment of inertia. This principle isn't just limited to ice skating. You can see it in action with figure skaters, divers tucking during flips, gymnasts performing aerial spins, and even when you spin around in an office chair with your arms extended and then pull them in. The conservation of angular momentum is a fundamental principle that governs all rotating systems in our universe.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.